Hello class, welcome to chapter 11 of the 40/40 course. This chapter is going to be about ANOVA, or Analysis of Variance. Before we start, a small disclaimer: you might have noticed that I got a new webcam and also a new mic. Hopefully the sound will be better now than it was on the previous videos. If it is not, please bear with me. I'll try to make it as good as possible, as fast as possible. So what do we learn about in this chapter? Well, we learn about using one-way analysis of variance, one-way ANOVA. What we use that for is to test for the differences between the means of several groups. We'll understand what that means in a second. Then we learn about two-way analysis of variance, two-way ANOVA, and we'll particularly insist on the interaction effect that can be revealed in a two-way ANOVA. So this is the plan for the lecture. First, we're going to talk about one-way ANOVA and F-test. And we'll touch on the Tukey-Kramer procedure, but very quickly. And then we'll talk about the two-way ANOVA with the F-test and the interactions effect. So right here, the pink boxes are what we're going to focus on most. What is the goal of ANOVA? The goal of ANOVA is to compare the means between more than two groups. So remember, in chapters 8 and 9, we learned how to test hypotheses about one sample. Then in chapter 10, we learned how to test hypotheses about two samples. Now we are talking about more than that. We are talking about three groups or more. So just to clarify things here, we talk about analysis of variance. It's called ANOVA, analysis of variance. But these are tests of the means. It's the procedure that we refer to as analysis of variance. But what we are testing is equality of means. Another important point is that this is extremely frequently used in experimental design. You will often hear scientists and engineers talk about how they used ANOVA. What is the general setting of ANOVA? Well, it's when you want to know whether a given variable is influenced by a given factor. The factor is also a variable. It's just a variable that has different levels. So you, as the investigator, you control one or more factors of interest. Each factor contains two or more levels. These levels can be either numerical or they can be categorical. But the point is that these levels define groups. And so you can think of these groups as a sample from a different population. So like I said, before we had just one sample, then we had two samples, and now these groups define things that you think of as 3 or 4 or 5 samples, or as many samples as you want. And so you observe the values of what you call the dependent variable, and the question is whether the mean of that variable is influenced by the factor. So for each group, you compute the values of the dependent variable, and does the mean of that dependent variable differ between the groups? Okay, so let's get started with one-way ANOVA. One-way ANOVA just means we have one factor, one dependent variable and one factor. So think about it this way. You have information about individuals or items. You have information that records the value of a variable. And then you have information that records the value of a factor, which is a second variable. It's a factor that defines 3 levels. And then all you have to do is think of the factor as dividing your sample into 3 groups. So for the first level of the factor, you make a subgroup. For the second value, you make a second group. And for the third value, you make a third group. And the question is simply, is the mean of the variable the same in all of the 3 groups? So here's a very simple example. People have been given a drug. They've been given the drug at 3 possible doses, 1 milliliter, 5 milliliters, or 10 milliliters, and we record their body temperature. So body temperature is our variable. The dose of the drug is our factor. It defines 3 levels, and so we define 3 subgroups of our body temperature variable. And we ask the question, is the patient's body temperature the same regardless of the dose that they received? And so in general, one-way analysis of variance allows us to evaluate the difference among the means of 3 or more groups. Here are some other examples. Maybe you're counting the number of accidents that happen during the first, second, or third shift at a factory. Maybe you want to know the expected mileage for 5 different brands of tires. All of these can be done with analysis of variance. You have 3 or more groups. Now, as always, for the math to work here, we need some assumptions. And these assumptions are that the populations are normally distributed, that the populations have equal variances, and that the samples are randomly and independently selected. These assumptions you should recognize. They sound very similar to what we used in chapters 8, 9, and 10. So ANOVA is a hypothesis testing method. We use it to compare H0 to H1, just as we did in the previous chapters. Now, what is the H0 of ANOVA? The H0 is that all the population means of all the groups or subgroups are equal. So mu1 equals mu2 equals mu3, etc., for however many groups you have. Another way of thinking about this is saying that there is no factor effect, meaning that no matter what level of the factor you are looking at, the mu is the same for your variable of interest. Now, what is our H1? Well, remember, H1 is always the mathematical opposite of H0. Now, what is the mathematical opposite of all of the mu's are equal? Well, it's simply not all of the mu's are equal. And if they are not equal, what does that mean? That means there is a factor effect. In other words, the mean of at least one of the groups is different than that of the other groups. Now, importantly, it does not mean that all of the population means for each group are different. It just means that at least one is different. Some groups may have the same mean, but at least one of them is different from the others. So graphically, what does this look like? Well, think about it this way. Before you distinguish any of the groups, imagine you have the distribution of your variable like this. This is the distribution of your variable of interest. This is the mu. Now, if H0 is true, what does that mean? That means that once you divide into groups, you still keep the same mu for each of the groups. So it means it looks something like this. No matter what group you're in, here we divide it into 3 groups, they all have the same mean. And so when the null hypothesis is true, it means that all the means are the same. There is no factor effect. So mu1 is equal to mu2 is equal to mu3 is equal to the original mu. Now, if H0 were to be rejected, it means you're imagining something like this. At least one of the distributions does not have the same mean as the others. So that's when the null hypothesis is not true. So if you reject the null hypothesis, you're imagining something like this. Or it could be something like that. It could be that they are all different. It could be that at least one is different from the others. That's right, it's just like in that Sesame Street song that you all know. One of them is different from the others. So importantly here, we are using the variation between the different groups to see whether their means are statistically different. So it's an analysis of variance, but the conclusions we make are about the means. So in practice, how do we actually go about doing ANOVA? Well, the way we do it is we partition the variation. What does it mean to partition the variation? So we divide the total variation in our sample, the total variation in our variable, into the variation due to the factor, so which group you belong to, versus the variation due to random error, which is all the other variation. Now, the first one we call variation among, so it's a variation among the different groups. And the next one is what we call the variation within. It's inside of each group how much variation there is. So this partition defines 3 types of variation that we're going to call the total variation, the among group variation, and the within group variation. Now, we refer to them as the SST, the SSA, and the SSW. What do the S's stand for? Well, they stand for sum of squares. Remember when we measured variation in the first chapters, we used the sum of squares meaning the sum of squared deviations from mean. And so here it's going to be the same thing. We use the deviation from means, it's just every time we're going to use a deviation that is slightly different. We're going to use a different mean as the reference. So our SST stands for the sum of squared total. Our SSA stands for the sum of squared among group. And SSW stands for sum of squares within. And in a second, I'll show you graphically what this looks like. So like before, these are all going to be sums of squares. So just as I showed in this picture, the total variation is divided into the variation among and the variation within. And so this means that SST is equal to SSA plus SSW, where again, it's the total sum of squares, the among sum of squares, and the within sum of squares. Okay, so let's tackle them one at a time. What is the sum of square totals? Well, we're going to introduce a little bit of notation here. We're going to say that J represents our group, and then I represents an individual in each of these groups, or an observation in each of these groups. And so now we define our observations as the Xij. So this is going to be the number of the observation inside of a given group. And the second notation we introduce is this X with 2 bars on top. So an X double bar is simply the mean across all of the groups. So the notation here again, C is the number of groups or levels, and we denote them by J's. Nj is the number of values inside of group J, and we denote them with an I, so it goes from I to Nj. And then the Xij is the ith observation of the jth group. And X double bar is what we call the grand mean, or the mean of all the data values. And so the sum of squared totals is just the sum over all of the groups, over all of the observations, of the difference between your observation Xij and the grand mean, the mean across all groups and values. Now wait a second. You might say that this just sounds like the regular sum of squares. It's the sum of squares for all of your observations compared to the mean of all of the observations. And you would be right. That's exactly what it is. This is simply the regular sum of squares. We just had to introduce these new notations because now we're thinking about different groups. But it is calculated exactly the same way. You can see that on this graph. If you imagine that these are your 3 groups, group 1 in green, group 2 in purple, group 3 in blue, the sum of squared total is simply the sum of the distances from each of these observations to the mean. Now we called the mean X double bar, and we refer to the X's with a group number and an observation number, but actually that's just the sum of squares as if you ignored all the groups. Alright, so now let's go to our second term, the sum of squares among. Now here again we have a bit of new notation, but you should understand what it means right away. So Xj bar is simply the mean inside of group J. As always, we add a bar to say this is the mean. So the sum of squared among is the sum over all the groups, over all the J's, of the square difference between the mean in the group and the overall mean. This is squared, and then also it is multiplied by Nj, the number of observations you have in each group. Graphically, what does this mean? Imagine you've divided your total sample into the red group and the blue group, and here is your first mean, and here is your second mean for the 2 groups. You are computing the difference between this mean versus the original mu, and the other mean versus the original mu. Of course, you don't know the mu, so you approximate it with X bar and X double bar, but that's what you're actually thinking about. Now we're going to introduce one more concept, which is the mean squared among. The mean squared among is just the SSA divided by C minus 1. So you can think of that as a SSA divided by certain degrees of freedom. And the degrees of freedom are the number of groups you have minus 1. Graphically, what does this look like? Well, If within the green group the mean is this, you calculate the distance from this mean to the overall mean. Then in the purple group, you calculate the distance between the purple group's mean to the overall mean. And then in the blue group, you also calculate the distance between the blue group's mean and the overall mean. And then you take these three distances, you square them, you multiply by the number of observations in each group, and that's your sum of squared among. Notice that here you don't take the distance between each individual observations and a mean. You just take the mean of the group versus the overall mean. Okay, and finally we have our third term, the sum of squares within. Well, you probably already are able to guess what that's going to be. It's going to be the same as the sum of squared, but this time you compare it to the mean of each group. So again, it's going to be xij minus a mean squared, but this time it's the mean of the group. It's the xj bar with just a single bar. It is the sample mean from group J. Graphically, what does that mean? Well, we are just considering every one of these J groups as independent, and then we're summing their sum of squares. And again, we introduce a new concept, the mean square within. And the mean square within is simply the SSW divided by degrees of freedom again, except this time degrees of freedom are n minus c. So that is the total number of observations minus the number of groups. And graphically, what does this look like? Well, it's just as if you calculated the sum of squared deviations from mean within group 1, then the same thing within group 2 against their own mean, and in group 3 against their own mean. And you summed all of that. So we've introduced 6 new concepts, the SSA, SSW, and SST, where SSA plus SSW equals SST. And those stand for the sums of squares. And now we've introduced 3 more concepts, which are the mean squares, and we have the mean squared among, the mean squared within, and the mean squared totals. In each case, the MS is just an SS divided by degrees of freedom, but be careful, the degrees of freedom are never the same. The degrees of freedom among are C minus 1, the degrees of freedom within are N minus C, and the degrees of freedom total are N minus 1. Remember, N is the number of observations you have, C is the number of groups you have. This table is probably the most important for you. This is what will help you answer questions when you're doing exercises in the lab. So in the rows here, we have the 3 different sources of variation, variation among, variation within, and variation total. These are the degrees of freedom associated with each. This is what we call the sum of squares associated with each. This is what we call the mean squares associated with each. I didn't show the mean square total because we don't really use it that much. Why do we not use it that much? Because the goal of ANOVA is to calculate this F-stat, and the F-stat is the MSA divided by the MSW. As you see, the MST is not here. Okay, so the goal of all of this was really just to compute this F statistic. Okay, this F statistic is the statistic that allows us to test the hypothesis H0. It's H0, remember, mu1 equals mu2 equals mu3, etc. All the mu's of all the groups are equal, versus H1, at least one of them is different from another one of them. At least 2 of them are different from each other, or at least one of them is different from the others. And so with this as our test statistic is the F-stat, which is MSA divided by MSW, the mean squares among versus the mean squares within. Like I said, each of them has degrees of freedom. First degrees of freedom is C minus 1, where C is the number of groups. The second degree of freedom is N minus C, where N is the total sum of all of your observations in all of the groups. How do you interpret an F statistic? You're going to be familiar with this. It's again the same as always. If the F statistic is high enough, meaning it's higher than a given critical value, which we will call F alpha, well, you can reject the null. Now again, just as in our 2 sample tests of the variance, we need to have this F stat be positive. Typically, the first degree of freedom will be very small because it's the number of groups minus 1. You may not have that many groups. And typically, the n minus c, the second degree of freedom, will be very large because that's the number of your observations minus the number of groups. Again, you may not have that many groups. Okay, so let's do an example. Imagine you're trying to test 3 golf clubs. So you shoot the clubs using an automated driving machine, for consistency, of course, and then you randomly select 5 measurements from each of the clubs to see how far the ball traveled. These were the distances with club 1, these were with club 2, these were with club 3. And so the question is there a difference in the mean distance that the ball traveled? So here is the data plotted out. This is club 1, club 2, club 3, and you see this is what defines our 3 groups. Here you plotted the distances, and that little bar is the mean, so that's x1 bar. Here, same thing, you got your 5 values and your mean x bar 2, or I should say x2 bar. And this is the mean of the third group, x3 bar. And the overall mean of all of these points is x bar bar, x double bar. If you want the values exactly, this is where they are: x1 bar, x2 bar, x3 bar, x double bar. So how would you compute an ANOVA? Well, you have your x1 bar, your x2 bar, your x3 bar, and your x double bar. All you need now is to compute your SSA and your SSW. That will then allow you to compute your MSA and your MSW. That will then allow you to compute the F-stat, which ends up being this. So for a little bit more detail, the SSA, the sum of squared among, this is the distance from mean 1 to the overall mean squared times 5, the number of observations in group 1. This is the mean of group 2 minus the overall mean squared times the number of observations in group 2. This is the mean of group 3 minus the overall mean squared times the number of observations in group 3. Here, all 3 groups have the same number of observations, but it doesn't have to be that way. And this is your SSA. The SSW, on the other hand, is the first point minus the mean of its group squared, plus the second point minus the mean of its group squared, etc., etc. Here, this is the last point minus the mean of its group. So this is the mean of group 1, this is the mean of group 3, because in these calculations, each point gets compared to the mean in its own group. The MSA and MSW are just the SSA and SSW divided by their respective degrees of freedom, number of groups minus 1, number of observations minus number of groups. Or the way we called them, this is C minus 1, this is N minus C. And the F-stat is just the MSA divided by the MSW, and it's equal to 25.275. So this should look familiar again. We're going to fill in this page and make our decision. So our H0 was mu1 equals mu2 equals mu3. Our H1 is they are not all equal. Alpha is 5%. The degrees of freedom 1 is 2. The degrees of freedom 2 is 12. Our critical value, which we got from an F table, is equal to 3.89. Remember, the F table had 2 degrees of freedom. And so what do? We compare our test statistic 25 to the critical value 3.89. Well, it's way, way, way larger, therefore we can reject. So our decision is that we reject H0 at alpha equals 5%. And so the conclusion is that we do have enough evidence to say that at least one of these groups has a mu that is different from the rest. This is what this ANOVA would look like in Excel. You don't see the data, but you see that the calculations are the same and the F-stat obtained is the same, as is the critical value. So if you did this in Excel instead of by hand, you would reach the same conclusion. Now, some of you may ask, okay, so we know that one of them is different from the others, but we don't know which one it is. And you'd be right, we don't actually know at this point. All that we know is that one of them is different. They are not all the same. So all you can conclude is this general point that they're not all the same. They don't all have the same means. There is some effect of the group, but we don't know what it is. And so how would we determine which of the group has a mean that's different from the other ones? Well, we would have to do something called a Tukey-Kramer procedure that does multiple comparison for the groups. And so I'm just going to say a word on the Tukey-Kramer procedure. I'm going to put the slides in that tell you exactly what the procedure is, and you can also go on Pearson, get the online book, and see how that procedure works, but I'm not going to teach exactly how to do it. That would take too much time. So the overall idea is that the Tukey-Kramer procedure tells you which population mean is significantly different from the others. This is something you do after you have already rejected your ANOVA. And so what it does is paired comparisons. So mu1 versus mu2, mu1 versus mu3, mu3 versus mu2. So the way it works is that you define a certain critical range, which is computed in this way. You can see the definitions here. I won't go over it. And so there are 5 steps in the procedure. First, you compute the absolute mean differences, like this. Second, you find this Q alpha value. And there's an appendix in your book that allows you to do that. In this case, with this data, the value is 3.77. Then you compute the critical range with this big formula that we're not going to go into. Critical range is equal to 16.285. And then you compare this critical range to these absolute values of the mean differences that you just calculated. So that is your step 5. You make your determination as to which pairs of means are different. In our case here, they are all different. Okay, so that concludes the first part of the lecture about one-way ANOVA. Second part of the lecture, two-way ANOVA. So what is two-way ANOVA? Well, it is kind of the same thing as one-way ANOVA, except in this case you have 2 factors of interest that determine your groups. So in this case you can think of it as having one variable and 2 factors, or I guess 3 variables, 1 variable that is your dependent variable, and 2 variables that define your groups. So we call them factors. So for instance, you could have the percent carbonation and the line speed as being 2 factors that affect your soft drink bottling process. And the key new questions that ANOVA allows us to answer is whether there are any interactions between the levels of the 2 factors. So does percent carbonation affect your bottling process? Does line speed affect your bottling process? And also, do they together interact when they affect your soft drink bottling process? In other words, does the effect of a particular carbonation level depend on how you set your line speed? So let's start from what we had earlier. We have a variable and a factor with 3 possible levels. Well, let's now just add a second factor with 2 possible levels. This defines how many groups? 6, because we have 3 levels of A, A1, A2, A3, and we have 2 levels of B, B1, and B2. And so in total we have 6 groups, A1, B1, A2, B1, A3, B1, A1, B2, A2, B2, A3, B2. And our first question is going to be, is the mean the same for all 6 groups? And if it is not, we're going to ask, are there interaction effects? A bit of vocabulary. A given combination of factor A and factor B levels, we like to call that a cell, and you'll understand in a second why it's called that. It's because when we cross-tabulate the 2, the values of one and the values of the other form a cell. So we would refer to A1B1 or A3B2 as cells of the possible factor levels. Again, we have assumptions similar as before. Populations are normal, populations have equal variances, and the samples are independently drawn. So two-way ANOVA functions the same way as one-way ANOVA, but we just now have more factors to think about. So we have 2 factors of interest, A and B. Let us call R the number of levels of factor A, C the number of levels of factor B. Remember, before we just had C as the number of groups, now we have R and C. And so, of course, the number of groups, the number of cells, is going to be R times C. Now let us call N the number of observations. So that is still the same as before. It's the entire number of observations you have in your samples. However, we now also have something we call n prime, and that is the number of replications for each cell. What does that mean? This is the number of observations we have in each group. And importantly, in this case, we assume that each AB combination, each cell, each group has the same number of observations n prime. That was not the case in one-way ANOVA, but now we have to assume that. Now our x's, in the previous chapters they were called xi, then in the previous section they were called xij, now we call them xijk, because we have the kth observation of level I of factor A and level j of factor B. Again, we are going to split total variation into components of variation. The exact same way that earlier we had SST equals SSA plus SSW, now we divide into 4 levels. We have SSA plus SSB plus SSAB plus SSE. So this is the variation coming from factor A, the variation coming from factor B, the variation coming from the interaction between A and B, and finally the remaining variation. And here in the purple squares you see the degrees of freedom associated with each of these sources of variation. So R-1 for SSA, C-1 for SSB, because R is the number of groups defined by factor A, C is the number of groups defined by factor B. For the interaction, it's R-1 times C-1. And finally, the one that is always the hardest to remember are the degrees of freedom for the SSE, the random variation, the error variation, the leftover variation. These degrees of freedom are R times C times N prime minus 1. Remember, N prime is this number of observations we have in each of the AB cells, in each of the groups defined by a level of A and a level of B. So let us jump straight into an example. Imagine this is the data on sales by location and availability of mobile payments. What does that mean? So this is the kind of data that store designers might be interested in. Where in your store are you making the most sales? Is it in the aisles, in the front, at the kiosk, or with an expert? And does the availability of paying with your mobile phone affect the number of sales that you make? So let's say you collected this data during 5 days. For each day, you collected the number of sales in each of these possible situations. In aisle, no. In aisle, yes. Front, no. Front, yes, etc. Repeated a few times. So how does that translate into an ANOVA situation? Well, let us call this our factor A. It's yes or no for mobile payments. Let's call this on factor B for location options. What is our N? Well, in total we have 40 observations, because that is 10 times 4. However, you can divide into groups by interacting factor A and factor B, like so. So this is a group, this is another group, this is a third group, etc., etc. What do we call these groups? We call them cells. What is a cell? It's a combination of a value for factor A and a value for factor B. Now what is N prime? N prime is 5, because we have 5 replications of each cell. In this cell, we have 5 values. In this cell, we have 5 values, etc. We have 5 values in each of these possible cells. Here are the equations of your two-way ANOVA. I'm not going to require of you to actually compute all of that by hand, but I'm showing them to you and I want you to have them available in the slides. The total variation is, of course, the same as always. It's the sum of squared total. It's a complicated formula, but it computes the same sum of squared errors that we always do in the entire sample. Variation coming from factor A is defined as follows. The one coming from factor B is defined as follows. Then we have this formula for the SSAB. So the variation that comes from the interaction between factor A and factor B. And finally, the sum of squared errors at the end is the leftover. Again, with our 6 groups, we still have something we call a grand mean. We still have means defined for levels of factor A means defined for levels of factor B and means defined for interactions of levels of factor A and levels of factor B. And each of our sums of squareds can also be converted to a mean squared when it is divided by the degrees of freedom. So there's mean squared factor A, mean squared factor B, mean squared interaction, and mean squared error. Now, how are we going to look at the results from a two-way ANOVA? Well, the first thing you're going to do is you're going to determine whether the interaction is statistically significant or not. If it is statistically significant, meaning if the interaction variation has an effect on your mean, then you will continue the analysis focusing on the interaction. However, if it is not significant, then you will forget about the interaction and focus on the main effects of each of the factors. How are you going to do that? Now, you're going to have three F-test statistics. There's the first F-stat, which is going to be MSA over MSE, so that is the F-test for the factor A effect. Then you're going to have the F-stat, that's MSB over MSE, that is the factor B effect F-test. And then you're going to have the third F-test for the interaction effect. That's going to be MSAB over MSC. Now, this looks complicated, but note that this is exactly the same as your first one-way ANOVA. It's just you repeat that 3 times for each of your factor A, factor B, and interaction. And each of those is going to be a test that you reject if the F-stat is greater than a given critical value. However, the hypothesis is going to be slightly different. In the first case, the hypothesis H0 is that the mu's are different across all levels of factor A. The second test looks at whether all mu's are equal for groups defined by levels of factor B. However, the third H0 is just whether or not there exists an interaction effect. So the H0 is that the interaction of A and B has an effect that is equal to 0, or it does not. Now again, this is the most important table for you to remember, so let's go over those elements. In the rows, the table disaggregates the different sources of variation. Factor A variation, factor B, interaction variation, error, and the total. It lists the different sums of squares associated to that, and the degrees of freedom associated with that. Here you have the calculations of the mean squared A, the mean squared B, the mean squared A and B interaction, and the mean squared error. Each time it is just the value in this column divided by the value in that column. And then finally you compute your F-stats. What are the F-stats? It's the value in this divided by the mean squared error. Then the second F-stat is the value here divided by the same mean squared error. And the value for the interaction is also the MSAB divided by the mean squared errors. Note that the denominator here is always the same for the 3 F-stats. Now I want to insist on this because you will have to do this in your homeworks and your exams. You will be given a partially filled two-way ANOVA summary table and you will have to complete it. Why do we ask you to do that? Well, because if you are given this, you should be able to fill in all of that, okay? So that will be one of the exercises you have to do, knowing how to compute the mean squares, how to compute the F-stats, and then make the appropriate decisions. Now, there are some clues that help you fill in those tables much faster, and those are as follows. The degrees of freedom always add up. So the total degrees of freedom, n-1, is always equal to the sum of degrees of freedom along that column. So to show this again, n-1, the number that ends up here, is always the sum of this plus this plus this plus that. Now the same is true of the sum of squares. The sum of squared totals is always the SSE plus SSA plus SSB plus SSAB. Again, you see that in the column right here, this plus this plus this plus that is equal to that, which means that if one of these terms is missing, you should be able to fill it out. If one of those terms is missing, you should be able to fill it out. And again, in that F-test column, the denominators of the F-test are always the same. They're always the SSE, but the numerators are different. So let us go back to this example just to remind you what data we had. We had factor A here, factor B here. We have 2 levels of factor A, 3 levels of factor B. Now I just want to show you what happens when you use this data to run a two-way ANOVA in Excel. The results look like this. Here you see your 2 levels of factor A, there are 4 levels of factor B. There's a whole range of statistics that are computed for you. Here the total statistics as well. And here your ANOVA output, which gives you the sums of squares, the degrees of freedom, the MS values, and the F values. You should recognize it. This is exactly the table that I showed you earlier with the 4 sources of variation, the sample sources, the column sources, the interaction, and the errors. Now notice that Excel does not give them the same names. Excel by default calls the factor A sample, calls the factor B columns, the interaction is the interaction, and then what we call the error, Excel calls that the within variation. Don't let this confuse you. Those are the same sources of variation in the same order as we discussed them. Last thing, how do you actually interpret those results? Well, as I said, you proceed in 2 phases. First thing, you look at the interaction terms and see, does the interaction matter or not? Here, in the interaction row, you see that the F is very small. It is way smaller than the critical value. So you fail to reject this one. What does that tell you? The interaction is not significant. Okay, now that you know that it is not significant, then you can look at the main effects. What are the main effects? These 2 F statistics. So first you looked at this F statistic, and only because you failed to reject do you start looking at these 2 F statistics. And these 2 F statistics, they're much bigger than their respective critical Fs, and so both of these factors have an effect on sales. A few words on the Tukey-Kramer procedure for a two-way ANOVA. It also exists. It is also done only after one or both of the factors have been shown to have significant effects. Again, I'm not going to tell you how these critical ranges are computed, but I'm going to show it to you so you have it for future reference. The way this works is again the same. You compute lots of differences in absolute means, and then you compute a critical range, and then for every one of these differences that is larger than your critical range, you can say that the mu's are different. Alright, so now in the last part of the lecture, we're going to talk a little bit more about these interactions. So the interesting thing is that these interactions can be visualized. They can be visualized with what we call a cell means plot. What is a cell means plot? It's simply a plot that shows the value of the means for each of the groups. Okay, so here, for instance, with our store example, here are the groups of factor B, and then we have 2 colors, one for each of the factor A's. No mobile payments versus mobile payments. And here what you see is that these lines are entirely parallel. Well, that is going to mean something to us. When these lines are parallel like this means that the interaction is insignificant. So to formalize this a little bit more, if you have interaction effects, this will yield plots that have non-parallel line segments. So if you see all the line segments that are parallel like that, this means no interaction. If you see that the lines cross, that will mean that there is some interaction. Why is that? Well, let's interpret an interaction effect. A statistically significant interaction indicates that the effect that one of your factors has on the dependent variable depends on what the level of the other factor is. And so in a cell means plot, this shows up as non-parallel segments. To understand this, let's do an example where we do have a significant interaction. So the question is, do ACT prep course type and course length, those are my 2 factors, do they impact mean ACT scores? Now we have the 2 factors, and we also want to check the interaction of the 2 factors. So here is our data. This is our A factor, traditional versus online. This is our B factor, condensed course versus regular course. And here is our data. If you plot the cell means for this data, you get the 2 lines that cross. These are the means for regular courses. These are the mean for condensed courses. The blue line is the traditional course, and the red line is the online course. So what does it mean that these lines are not parallel? Well, it means that the effect of condensing the course will depend on whether the course is taught in a traditional classroom or online. You can follow it this way. If you take a regular course in a traditional classroom and you condense it, that decreases the means. If you take an online course that is of regular length and you condense it, that increases the ACT score. So this means that the effect of condensing can be to increase or it can be to decrease, but that depends on whether your course is traditional or online. And so that's why we call this an interaction effect. In Excel, what would this look like? You would reject the null hypothesis of this test, the third line, the interaction f-test. You would have the f-stat larger than the critical f-value, or you would have a very low p-value. Remember, that is just an alternative way of looking at your test. So here the interaction between the course length and course type is significant. Now, one thing that is very important is that if you do reject the third hypothesis, the interaction hypothesis, then you cannot say anything about these first two, okay? You always have to do it in that order. You first look at the interaction f-test, and only if you fail to reject the interaction f-test do you become interested in those other two. Otherwise, you drop these, you cannot say anything about them. So what would you do if you did have a significant interaction term? Well, what you can do is you just collapse the data into just 4 groups, and then you treat them as if it was a one-way ANOVA. For instance, here, you would just make new groups called traditional condensed course, traditional regular course, online condensed course, and online regular course. You have 4 groups, you can run a regular one-way ANOVA. And so we are at the end of the chapter. What did we look at? We saw how to use one-way ANOVA to test the differences among the means of several groups along one factor, how to use two-way ANOVA to do the same thing with 2 factors, and then we looked at the interaction effect. And here is your joke of the day. This top part, this is the joke for old people like me, and here apparently this one works better for your generation. Enjoy.